Here we're asked to find the instantaneous rate of change at along different points, x equals 2, x equals 8, and x equals 15. Of course, the easier route to go, rather than to have to calculate the definition of the derivative 3 separate times, we're going to do it once and then just go ahead and plug in our 2, 8, and 15. So what we would like to do is we would like to find the slope function. Here it is in all of its infinite glory. And we want to figure out what the instantaneous rate of change will be as the horizontal distance between the points approaches 0, and we want to be able to identify the limiting slope. So we're going to find our pieces first. Piece 1 is fairly straightforward. We just have to copy it down. This is a step that you can really skip in doing this general derivative equation if you want. But some people just like to have it all down before they plug it in. And then secondly, we'll do f of x plus h, which asks us to plug in this anywhere I see an x. So I will have x plus h squared minus 2 times x plus h plus 3. Okay, so that means that if you FOIL this thing out, now remember you can't just do x squared plus h squared. This means x plus h times x plus h, you get x squared plus 2xh plus h squared. And then over here we'll distribute our negative 2 to get negative 2x minus 2h, and then we have our plus 3. Now there are no like terms we can combine. They're all different. They have a different number of x's and h's and a different exponent of the x and h. So we can't do anything there. So we're ready to go ahead and plug everything in. So we will have the limiting slope as h approaches 0 of x squared plus 2xh plus h squared minus 2x minus 2h plus 3. And we're going to subtract away this guy here, so we can't forget to put our parentheses, x squared minus 2x plus 3. All over, that's a long thing, x plus h minus x, the x's cancel, and we just have h on the bottom again. Remember, the h is just basically saying that that's the change in x. That's how far the two x values are from each other. Now, one thing you might notice, here's a little trick. The little trick is, since you're going to be taking number 2 and you're going to be subtracting from it number 1, you can actually just go through and you can look at variables or terms of these expressions, and if they have the same sign and then they're the same quantity, you can actually cross them out here. So x squared, negative 2x, positive 3, because really all I do when I write it down is now I distribute the negative sign. That switches the sign to the opposite, and so now I cancel x squared with negative x squared, negative 2x with positive 2x, and positive 3 with negative 3. And so you can kind of save yourself that time if you cancel out before you write it down. But you don't have to do it that way. That's just a little kind of a time-saving trick. And so we have 2xh plus h squared minus 2h. So you might want to cross things out as you go to make sure you have written everything down. And that's it. That's everything on top. Now notice again that the beauty here is that every term now has an h, whereas before the 2x and the 3 didn't contain an h. So this will allow us to factor out an h from the top so that we can cancel it with the h in the bottom, and that helps us accomplish our goal of being able to make h 0. So that goes away, and I'll finish up right up here. That gives us the limit of the slope as h goes to 0. Now keep in mind, this thing here, this quantity is still a slope. This is still a rate of change. We're going to make it instantaneous by making the distance between the 2 points 0 now. Because keep in mind, all we've done, these are all equal to each other. We're just going step by step and we're reducing things. This is still a slope, but now I'm going to make the slope, the difference between the 2 points 0. I'm going to remove the limit sign because I've taken care of that. My reminder has reminded me. And I get 2x minus 2. So this 2x minus 2, if I start plugging in numbers for x, will generate slopes. It will tell me what the slope is at those particular input values. So we want 2, 8, and 15. We want f prime of 2, f prime of 8, and f prime of 15. And our function was, to remind myself, 2x minus 2. Go to the next page. So we'll do 2 times 2 minus 2, which is 4 minus 2, which is 2. 2 times 8 minus 2, which is 16 minus 2, gives us 14. And f prime of 15 is 2 times 15, which is 30, minus 2 is 28. Now remember, this is a rate of change now. This is not an output. I mean, it is an output from this equation, but this represents a rate of change. So this is change in y units per change in x unit. Excuse me, I shouldn't say change in y units. I should just say 2 y's for every 1 x. 14 y's for every 1 x, and 28 y's for every 1 x. So if I were to sketch this thing, what I could do is to say, all right, well, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now this is not really enough rate of change to really sketch the original function, but when the input is 2, and I don't know where the output is right now based on the slope, but let's just suppose it's here. I get a slope of 2, so not a very steep one. But now as I get over to f prime of 8, 3, 4, 5, 6, 7, 8, now I have a line segment that has a very steep slope, a slope of 14. So it looks kind of more like this. So if I can kind of see that what appears to be happening is some sort of curvature. And then when the input's 15, I'm going to get something that's really, really steep, which is more like that. So I can kind of see the general shape of this thing. Looks like it is concave up. Now that doesn't really, if I don't know what the function looks like, I don't necessarily know what kind of concave up, but this at least helps me to visualize what's happening.